In the lecture on logic, we have seen several what we call logical connectors. We have seen the AND. Okay, so if you have two formulas, P and Q, then P and Q is true only if P is true and Q is true. And you have seen the OR, which means that P or Q is true, if and only if P is true, Q is true, Q is true, or they're both true. And then you have seen the NOT, which basically negates a formula from true to false and from false to true. And you have also seen the implication and then the equivalence. So these logical connectors have actually an application when it comes to electronic circuits. So here I have this is called a beadboard, so it's used to make very simple electrical circuits. Okay, and you can actually buy these gates into chips. So this is a chip that contains, I think, something like 4 AND gates. Okay, so you can connect these pins here on the chip. For example, the first 3, if you put an electrical current of say 5 volts on chip 1 and chip 2, then the third pin here, if you put 5 volts on pin 1 and pin 2, that the third pin will also output 5 volts, right? So this is an AND. The third pin will also only output if you put volts on the first and the second one. Then the second chip is an OR chip, or it contains a number of OR gates. And then the third chip that we see here is an inverter. Basically, it takes in a value and gives the opposite value. So what I've done here is I've built a small circuit in order to demonstrate this. So I have 2 switches, which is here, and I have a switch here. And so first, what I did is I connected them to the AND gate, and the output of the AND gate I connected to this LED here. So if everything is correctly, this light should only go on if I give input 2 times an input to this chip. Okay, so if I only push the first button, nothing should happen, which is the case. If I only push the second one, nothing should happen. But if I push both of them, then as you see, the light turns on. Okay, so this is an AND gate, which works like this. The second light is connected to an OR gate. So let me first disconnect the one for the AND and try to make sure that I make no errors for the second one. So here I have an OR gate, so it should light up as soon as I click one of the 2 switches. Okay, so if I click this one, it lights up. If I click this one, it lights up. And of course, if I have both of them, it also lights up. Okay, so this is the OR gate that you have here. And then the third one is for the inverter. As you see, I'm not clicking any button, but it already lights up, right? So I'm not giving a pulse here, but it inverts the non-pulse into a pulse, so you get light. And the light should go out whenever I click this button. Okay, so if I don't click it, it lights up. If I click it, it doesn't light up. Okay, and then the fourth one is the implication that we have seen. So what I've done is so if this is P and this is Q, then you have P implies Q. So you know that P implies Q is the same as not P or Q. Okay, so what I did, I inverted the first one to this using this chip, and then I ORed it, right? I make the OR with this chip using an OR gate in this one here, and then the output I connected to this light here, right? So now P is false, so you see that P implies Q is true. So if I make P true, right, then P is true but Q is false, so the implication is not valid. Okay, if I only press Q, then P is false and Q is true, so the implication holds. And if I click both, I still had the AND gate correct, so you see it lights up, right? So the only time it doesn't light up is if P is true and Q is false. So these electrical circuits can actually be made, are used in computers. And let me give an example of some kind of electronic circuit, or logical circuit, I should say, that's often used in computers. In particular, it's used to store values in a computer, right? So if you run a computer program and you assign, for example, a variable x has the value equal to 5, then your computer should store this value in memory, okay? And you can ask yourself, okay, how can a computer store something in memory? It has to change the switch or something, right? So how do you make a switch using logical connectives? That's not super easy because your computer is not mechanical, okay? It's only electrical impulses. And in order to do this, the computer makes use of something that's called a NOR gate. Okay, so a NOR gate is nothing else than a not or gate. Okay, so if I have a formula P and a formula Q, then the NOR is the same as not P or Q. Okay, and you know that this is the same as not P and not Q. Okay, so it only has the value 1 if both P and Q are false. Okay, so let me draw the circuit that the computer uses, and then we will analyze how it actually behaves. So we have two NOR gates. Okay, so let me draw one here and draw one here. So a NOR gate needs to have two inputs, a P and a Q. Okay, so let me write the inputs here. So it's an input here, and then it needs to have an input here, and the second one needs to have an input here and an input here. And then let's assume that the computer stores something as a light switch or something, right? So this is a LED, okay, and then there's an electrical circuit connected to this. And how do we make the circuit? Well, we take the output of this NOR gate and put it in as an input of this NOR gate, take the output of this NOR gate and put this as an input of this NOR gate. Okay, so this is close, it's not exactly, but this is close to what in logical engineering is called a flip-flop, and you will see in a minute why this is called a flip-flop. Okay, so the only thing that we can do something about is this input here, let's call this P, and this input here, let's call this Q. Okay, so we can put P equal to 0 or 1, or we can put Q equal to 0 or 1. So let's try to make a truth table, right? So we have P and Q. So it can be 0 0 0 1 1 0 or 1 1. And let's see what happens. So the easiest cases to analyze are this one and this one. So let's start with these two. So first assume that P is 0, right? So we have 0 here, and that Q is equal to 1, so we have an input of 1 here. Okay, so this is a NOR gate, so its output is equal to 1 only if both inputs are false. Okay, so we have this one here. So here, not both inputs are false, right? Because Q is 1. Okay, so the output, whatever it will be equal to 0. Okay, so the light will not burn. Okay, so if we here have the light here will be equal to 0. Okay, this 0 goes in here into this NOR gate. Okay, both inputs are false, so the output here will be equal to 1, and we will have a 1 here in this case. Okay, so this is the first state. Here we have both 1s, so the NOR will give you 0, this 0 0 gives you 1. So this thing is in, you can call it equilibrium, right? It's in equilibrium and the light will not go on. So this is a stable configuration. Okay, so let me draw the same circuit again. Okay, we have Q, we have, sorry, this one goes to this output. The output here goes to the input here, and here we have P. So let's now, we had 0 1, let's now consider 1 0. Okay, so P is 1 and Q is 0, and the analysis is very similar to what we had before. So here for this one, it cannot be the case that both are negative, right? So here the output has to be 0. Okay, so if I have a 0 and a 0 here, 0, 0 with the NOR gives you 1, and this gives you 1, 1, 1 gives you 0. So if I have a light bulb here, in this case, you have a 1, right, with the light bulb, so here the light will burn. Okay, so here we have a 1. Good. So let me, maybe I should draw the circuit again on this piece of paper. Okay, so we have a NOR gate here, a NOR gate here, Q, P, output here, output here, output here. And let's now take the case where both P and Q are equal to 0. Okay, so here P is equal to 0 and here Q is equal to 0. So here we have 0 and something. For the moment we don't know what the something is going to be because it's going to be the output of this NOR gate. So if this something is 0, so basically we don't know what's going to happen here, and we don't know for sure what's going to happen here, right? So we have to make some assumption on the value of this input or this input. Okay, so for example, assume that here this input is equal to 1. Okay, so this is case 1. Let me draw it in green. Okay, so you can see case 1 should be the green case, and then we will consider case 2 to be the other one. So if you have 0 and 1, then it's not the case that both are false. Right, so here we will have a 0 as output, the light will not burn, and then the 0 will be 0 here. We have both zeros, this will be converted into a NOR of 1, and this is what we had before, right? So this is a stable equilibrium if this would be equal to 1. Okay. Now, it's also the case that this could be 0, right? So let me write it in black here. So what happens if this is 0? Then both inputs are 0, so this input becomes a 1. Okay, so the light will burn. And then this input is of course 1, and the one with 0, the OR is 1, so the NOR will be 0, and this is compatible with the 0. Okay, so depending on whether initially this is a 1 or a 0, we will have a light burning or not. Okay, so here we have no idea whether the light will burn or not. So basically, if the light burned beforehand, right, so this means that if the light, so if you look at these diagrams, let's assume that the light was burning, right, and suddenly we switch off the P here, then the P and the Q will be 0, 0, so we are in this case. So if the light is initially burning, then here the input will be 0. Okay, so we are in the 0, 0, the light will burn, and the state will still be stable. Okay, so initially when the light was burning, if you go to 0, 0, it will still be burning. If the light was out, then initially we had 1 here. If we change the Q from 1 to 0, we arrive at this state here with the green case. Okay, so the light will stay out. Okay, so if the light was initially burning, one of these two cases, if you go from here to here, the light will still be burning. If the light was initially out, we go from here to here, then the light will stay initially out. Okay, so depending on whether the light is on or off here, if I go from 0, 1 or to 1, 0, the light will not change status. And this is how we can get something into to memory. So we have a last case where both inputs are equal to 1. So let's see what happens in this case. So we have the two NOR gates. This one goes here, this one goes here. It's a bad drawing, sorry. So we have Q, P, and we have our light bulb. Okay, so assume that both are equal to 1. So we have a 1 for Q, a 1 for P. So this is a NOR. So whatever the input, the second input will be with P, you have OR is true, so NOR will be false. Okay, so here we have a 0. Here we have also 0, 1, 0. OR gives you 1, output will be 0, and this will be 0 here. Okay, so there's also one stable configuration for both 1, and that's that the light will be out. Okay. However, this case is not super interesting. So normally in an electrical circuit, logical circuit in a computer, either Q will be pressed or P will be pressed, but it's rarely that they will both be pressed. Okay, so normally you go from state here to state here, and then from here to here, and then from here to there, but the last case will rarely occur. But it's still interesting to see what happens. Okay, so here I have my breadboard. I have my two switches, the P and the Q. I'm not sure which one is which, but it doesn't matter. To my I have a chip, and this is a NOR chip, not OR gates. Okay, so I have wired this up, and the output is here, this LED that you see. So the LED is out at the moment. So what would happen if I push this button? And you see that nothing happens, right? So the LED is out, I can push this button all I want, nothing happens. So what happens if I push this button? Now the light burns. So I've basically pushed my P. This is my P in my example. I pushed the P and the light burns. If I push it again, nothing happens, the stays in memory, okay? But now if I push the Q, the light goes out again. Okay, so I can set something in memory. I can set it again, it will not change. It will stay in memory as long as I want. I can leave all buttons alone. If I want to take it out of memory, I push the other button. I can push it all I want, it stays out of memory. All right, so in circuits, this is called the set button, and this is called the reset button. So you set a value, and then you reset it once you no longer need it.